Today we are going to learn about mastering stratified K-fold cross validation. You will discover how to implement this method using Python, especially in the context of imbalanced datasets, and how it can improve the accuracy of your model evaluations.
Welcome to our exploration of stratified K-fold cross validation. In this video, we'll delve into how this technique can be a game changer for model evaluation, especially when dealing with imbalanced datasets. We'll cover its definition, importance, and application in Python. By the end of this session, you'll be well equipped to enhance your model's evaluation accuracy using stratified K-fold.
Cross-validation is a statistical method used to estimate the skill of machine learning models in practical settings. Its primary purpose is to provide a robust assessment of a model's prediction performance. The basic idea involves splitting your data into two parts, one for training and the other for testing. By doing so, you can evaluate how well your model performs on unseen data. Traditional techniques include methods like holdout, but K-fold cross-validation is one of the most widely adopted approaches due to its balance between bias and variance. It involves dividing the dataset into subsets, or folds, and then iteratively training the model on two of those folds while testing on the remaining one. This ensures that every data point gets to be in a test set exactly once and gets to be in a training set key times, providing a thorough evaluation framework. Today, we'll extend this concept by introducing stratified K-fold, which maintains class distribution in each fold, crucial for imbalanced datasets.
Stratified K-fold cross-validation is an enhancement of the basic K-fold method. Its primary goal is to ensure that each fold has approximately the same percentage of samples of each target class as the complete set. This is particularly important when dealing with imbalanced datasets, where certain classes may be underrepresented. In a regular K-fold approach, the random assignment of samples to folds can lead to a situation where some folds have a disproportionate number of samples of certain classes. This can skew the evaluation metrics and lead to misleading conclusions about the model's performance. By using stratified K-fold, we maintain the class distribution across all folds, leading to more reliable and robust evaluation outcomes. This technique is not only beneficial but often necessary when working with real-world datasets that have imbalanced class distributions. In the world of machine learning, imbalanced datasets are a common challenge. They occur when the classes in the dataset are not represented equally. For instance, in a medical dataset, the number of positive cases, for example, people with a disease, might be much smaller than negative cases. This imbalance poses a significant problem for training machine learning models. If not addressed, a model might simply predict the majority class all the time, leading to high accuracy but poor performance on the minority class. Stratified K-fold cross-validation addresses this issue by ensuring that each fold in the dataset maintains the same class distribution as the original dataset. This stratification ensures that during model evaluation, every fold is a fair representation of the entire dataset. Consequently, this leads to more accurate and reliable performance metrics, providing a clearer picture of how the model will perform on unseen data. Comparing regular K-fold and stratified K-fold cross-validation reveals critical differences, especially in terms of class distribution. Regular K-fold divides the dataset randomly into K subsets, which can lead to uneven distribution of classes across the folds. This uneven distribution can significantly impact evaluation metrics, particularly in datasets with imbalanced classes, resulting in biased evaluations. On the other hand, stratified K-fold ensures that each fold is a representative mini-version of the full dataset, maintaining the original class proportions. This is especially crucial for binary or multi-class classification problems where class imbalance is prevalent. While regular K-fold is suitable for balanced datasets or when stratification is not necessary, stratified K-fold is the preferred choice for imbalanced datasets to ensure fair and reliable evaluation. The advantages of stratification include more accurate performance metrics and a better understanding of how the model might perform on each class in real-world scenarios.
Let's dive into the practical implementation of stratified K-fold cross-validation using Python. First, ensure you have Python installed on your system, along with the necessary libraries such as NumPy, Pandas, and scikit-learn. Begin by importing the libraries. Import NumPy as NP, import Pandas as PD, and from scikit-learn.model_selection import stratified fold. Next, prepare a dataset to work with, which can be a CSV file loaded using Pandas, data equals pd.read_csv or _dataset.csv. Now, define your features and target variable, x equals data.dropTarget, axis equals 1, y equals data target. Initialize the stratified K-fold object, skf equals stratified fold n_splits equals 5. Then, iterate over the folds using for train_index, test_index in skf.split x, y, and create train test splits, x_train, x_test equals x.illic train_index, x.illic test_index, y_train, y_test equals y.illic train_index, y.illic test_index. Now, you can train your model on x_train and y_train, and evaluate it on x_test and y_test. Finally, analyze the results to assess the model's performance across different folds, ensuring consistent and reliable evaluation.
Scikit-learn is a powerful Python library for machine learning, providing easy-to-use tools for data analysis and modeling. One of its features is the Stratified Fold class, which facilitates the implementation of Stratified K-Fold Cross Validation. To use this class, start by importing it. From scikit-learn.model_selection import stratified fold. Initialize the object with the desired number of splits. skf equals stratified fold n_splits equals 5, shuffle equals true, random_state equals 1. The shuffle parameter ensures random shuffling of data before splitting, and random_state guarantees reproducible output.
With the object initialized, you can loop through the folds using split method, for train_index, test_index in skf.splitx, y.
This gives you indices for training and testing data. You can then use these indices to create train test splits and evaluate your model's performance on different subsets of the data. By leveraging Stratified Fold from scikit-learn, you ensure a structured and balanced evaluation process, leading to more accurate and reliable model performance metrics.
To illustrate the implementation of Stratified K-Fold Cross Validation, let's work with a practical example using a real-world dataset. Choose a dataset that demonstrates class imbalance, such as a medical dataset where the target variable represents the presence of a disease. Begin by loading the dataset using pandas, data equals pd.read_csv medical_data.csv. Conduct necessary pre-processing, such as handling missing values and normalizing features. Define your features and target, x equals data.drop disease, axis equals 1, y equals data disease. Initialize stratified fold, skf equals stratified fold n_splits equals 5. Iterate through the folds. For train_index, test_index in skf.splitx, y, and create train test splits, x_train, x_test equals x.illic_train_index, x.illic_test_index, y_train, y_test equals y.illic_train_index, y.illic_test_index. Train a classification model, such as a logistic regression, from scikit-learn.linear_model import logistic regression, model equals logistic regression, model.fit x_train, y_train. Evaluate the model's performance using metrics like accuracy, precision, and recall. Analyze the results across different folds to ensure consistent performance and reliability. This practical example demonstrates the power and importance of Stratified K-Fold Cross Validation in real-world applications. Evaluating the performance improvements achieved through Stratified K-Fold Cross Validation involves a detailed analysis of various metrics. Begin by comparing the results obtained using Stratified K-Fold with those from regular K-Fold. Focus on key metrics such as accuracy, precision, recall, and F1 score. Stratified K-Fold tends to provide more reliable and consistent metrics, especially in the presence of class imbalance. The stratification process ensures that each fold is representative of the entire dataset, leading to a more accurate assessment of the model's true performance. This is particularly important for binary and multi-class classification tasks where certain classes might be underrepresented. By analyzing the results across different folds, you can identify any potential overfitting or underfitting issues and gain insights into the model's robustness and reliability. Overall, the use of Stratified K-Fold Cross Validation leads to a more thorough and realistic evaluation of your model, providing a clearer understanding of its capabilities and limitations.
While Stratified K-Fold Cross Validation is a powerful tool, there are common pitfalls to be aware of. One major issue is data leakage, which occurs when information from the test set inadvertently influences the training process. To avoid this, ensure that data preprocessing steps like normalization or feature selection are performed within each fold, not on the entire dataset. Handling missing values can also pose a challenge. Decide whether to impute missing data within each fold or exclude samples with missing values altogether. Ensuring balanced folds is another critical aspect. Always verify that each fold maintains the class distribution of the full dataset. For small datasets, consider reducing the number of splits or using techniques like bootstrapping. Finally, troubleshooting common errors often involves checking the compatibility of data types and ensuring that the scikit-learn version supports the implemented features. By being aware of these pitfalls and implementing solutions, you can maximize the effectiveness of Stratified K-Fold Cross Validation in your model evaluation process. In conclusion, Stratified K-Fold Cross Validation is an essential technique for model evaluation, particularly when dealing with imbalanced datasets. It ensures that each fold maintains the class distribution of the entire dataset, leading to more reliable and accurate performance metrics. Throughout this video, we've covered the theoretical background, practical implementation in Python, and the significant improvements in model evaluation that Stratified K-Fold offers. By applying the insights and techniques discussed, you can enhance your machine learning model assessments and achieve more dependable outcomes. We encourage you to practice implementing stratified K-fold on your datasets to experience its benefits firsthand. Thank you for joining this educational journey into mastering stratified K-fold cross validation.